You are given an array of length n, and let us consider the prefix maxima for this array. So prefix maxima is nothing but you go from left to right and you track all the maximas that you see. So the first maxima that you see is 10. So you label 10 over here. So this is 10. And then you will see that the prefix maxima does not change because the prefix maxima for this block is 10, and for this block is also 10. This block is also 10. And this is the first time you encounter 20 as the prefix maxima. So this you label it as 20. So this is 10, this is 20. Then you keep going to the right, the prefix maxima does not change until at this point it jumps to 30, and you can see that the prefix maxima will always be non-decreasing. And then you keep going to the right and then you eventually hit 40. So these are the elements that do not change the prefix maxima, and this is 40. And then you keep going to the right and then you hit 50. So you will see that this prefix maxima creates this sort of pattern where you have one unique element, and then for some reason it does not change. Then you have another unique element, and which of course will be higher than the previous element. That is why it is an increasing line graph. And then for some reason it will not change, and then you will have some higher element and so on. So these unique elements that you see on the prefix minima graph, like 10, 20, 30, 40, and 50, let us consider this as the unique prefix maxima. Let's define a new sequence for a given array A. So this is the array. You define a new sequence that contains all the first occurrences of the prefix maxima, which will of course be sorted, as you can see. So this is the unique prefix maxima. So your goal is to find out that given this array, how many subsequences are there how many subsequences are there that can produce this same set of boxes. So in any subsequence that you consider, you should have this exact same colored boxes, ignoring all the white lines. So white lines are basically the regions where the prefix maxima does not change. For example, if you select this subsequence 10, 9, 5, and then the rest of the thing, then also you will see that this subsequence where you have excluded one, this will also create the same colored boxes. Why? Because the prefix maxima jump will again be 10, 20, 30, 40, and 50. But you can see that if you decide to leave out this 20 from your subsequence, then your prefix maxima jump will not be optimal. So it will create something like 10, 20, 10, and then it will directly jump to 30. Not directly jump to 30, it will just go to 10 to 11, which is the wrong colored box that you have gotten over here. So you have to come up with an algorithm to compute how many subsequences are there in this string. There are a total of 2 to the power n subsequences, but how many valid subsequences are there that can produce this same set of unique prefix maxima. So all the elements that you see over here, it should appear in the subsequence, and this should create a prefix maxima. So there should not be any additional box that arrives over here. So it is a necessary and a sufficient condition in that sense. So how do you solve this problem? Now looking at this problem, of course this is a counting problem, and you might get the intuition that it can be solved via DP, and of course it will be solved via DP. But how do we define the states? How do we define the transitions? So in most of these DP problems, you have to start thinking about your choices when you have computed the answer for something and you want to add one additional element. So assume that you already have the answer for an array of length n. If I give you how many unique subsequences are there for an array of length n such that they produce the same colorful block. So this is the sequence of the prefix maxima. So if I tell you how many subsequences are there for this n elements that produce this block, can you figure out what will be the total count of subsequences when you append just one element at the end? Suppose this element is Z, the element that you are trying to insert, trying to append. Now, there are two choices. In your final subsequence, either this element will be part of your subsequence or it will not be part of your subsequence. So you have two choices. You can either take this element or you can either leave this element. So if you decide to leave this element, then of course the answer is the number of unique subsequences that you have, number of distinct subsequences that you have created from these first n elements, that will be the answer. So suppose you define that as dp of n, let's say dp of I represents the answer for this. Now what happens when you decide to take this element? So if you know all the subsequence that creates this block, and you can see that it in this blocks all elements are assigned a level. So this is level 1, this element is on level 2, this element is on level 3, level 4, and this is on level 5. Now if I just tell you the number of subsequence that create these blocks of 5 levels, is that sufficient for you to figure out whether taking this element is allowed or not? You will realize that it is not sufficient, because what if you have already constructed this block and this element that you see over here, suppose this becomes greater than this element, then it will now start adding one more box over here, which you don't want. So therefore it is not enough for you to know this subsequence count. You also need to track one more parameter to determine whether you should take this element in your set or whether you should leave this. So what do you think that parameter will be? You will have to track the level that you have reached with this subsequence so far. So this time let's track the level of the subsequence. Level of the subsequence basically means that the subsequence that you have created, what is the last unique prefix maxima that you have obtained in your subsequence so far. So we will modify this DP definition, and this time we will say that let's say something like DP of level represents the number of subsequences created by the elements seen so far, such that the last prefix maxima is at level L, let's say. Now how does this help us? So this time you can see that there, in the worst case, there can be n different levels, right? And suppose you want to append an element, this is the subsequence that you are dealing, this is the original array that you are dealing with, and you must have constructed various subsequence of different length. One subsequence can be of length 2, one subsequence can be of length 3, one of length 9, etc. But all of them can be classified into some different levels. So there will be k different levels. And what are these levels? So levels you basically define as the first occurrence of the prefix maxima in the array. So these are the levels from 1 to 5. Then what happens when you try to append an element into the sequence? You are trying to append an element over here. Then there will be some subsequence that end at this level, some subsequence that end at this level, some subsequence that end at this level, some subsequence that end here, and some that end over here. And you can see that all of these levels are sorted because these are prefix maxima, so of course it has to be in increasing order. So suppose the number that you are trying to insert is x. So consider all the subsequence, and so since this is a sorted subsequence, let's locate where x should fit. So if this prefix maxima, if this is the first prefix maxima that is greater than x, this means that in all of these subsequences, can you append x? No, because if you append x, it means that x is greater than this, greater than this, greater than this. It means that x will directly lead you from this level to something higher. So this means that you will miss the chance of taking these elements in your subsequence. Therefore, you can see that if the last element that you have taken, suppose the last prefix maxima, if the last prefix maxima if it is less than x, then you can only take this element x if it is equal to this level. This means that if you have this increasing subsequence of prefix maximas, let's say, and if this jump leads you to this one, then you can start a new level. So basically you can go from level L to level L plus 1, but you should not be jumping levels. But what about the other case where, let's consider the other case where this is, all these elements are greater than x, and you are at, suppose you are at this level. For all the subsequences that you have computed, you are at this level. And what happens if x is smaller than this green box that you see over here? So if x is smaller, you can see that if you place x over here, this green box will still be the prefix maximum because this green box is bigger. So this means that if the last maxima was greater than x, then our strategy is simple. You can take that element if you want, and your level will not change. If last prefix maxima is greater than x, you can take it and your level will not change. Even if it, in fact, even if it is equal to x, then you can take it and your level will not change. But if it is smaller than x, then you can only take it if the jump takes you from level 1 to level 2. So you have already stored the value of each of the boxes that you see over here somewhere, right? So you can see whether the incoming x, is it equal to this blue box or is it equal to this green box. If it is equal to this blue box, then you are not allowed to take it. But if it is equal to this green box, then you can take it and then you can increase your level by 1. So the DP transitions would become that you iterate over all the elements. You have already constructed the answer for this array so far, and you want to find out the answer when you want to insert an element. So you store the answer in a levels array, like let's say this is the level, and level of I denotes the answer when all such subsequence end at level I. And then this is the levels array, suppose. So there will be some elements that are smaller than x, there will be some element that is equal to x, and then there will be some element that is larger than x. So for all the elements that are greater than x, right, all these elements greater than x, this means that all these subsequences end at a level whose value is greater than x, right? This means that you can freely take x and your prefix maxima will not change. So you have both the choices. You can either take it or leave it. But for all the elements that are smaller than x, you only have to see whether this jump will lead you from this level to the next level. And if so, you increase the level count by 1. So now let's look at the implementation. So given the original array, you compute the levels. So there will be a total of, the number of levels will be equal to the number of unique prefix maximas that you see, right? So this code basically, it traverses through the entire list and computes these colorful blocks that you see. So this is the first prefix maxima, second prefix maxima, third prefix maxima, fourth prefix maxima, and the fifth prefix maxima. And so it stores all of these prefix maximas in an array in a sorted order so that you can quickly do some lookups on it. Now you start appending elements one by one, right? So in your DP, you have already constructed the answer for I is equal to 0 to n minus 1, and you are interested in knowing what will happen if you want to insert element AI. So first of all, you have to find out which levels are greater than AI. Suppose these levels are greater than AI and these levels are smaller than AI. Then all the levels that are greater than AI, you can simply append X to it and their level will not change. So that is why you have both the choices there, right? So if the number of subsequences that you have created so far is Z, so you can either keep that subsequence as it is, or you can create a new subsequence called Z comma AI that you just appended. So that is why we multiply it by 2. But what if the element that you are trying to insert is taking you from this level to the next level, right? Because you just looked for the element that is bigger than or equal to this element. If it is so, then you can decide to take that element, right? So if you decide to take that element, then the number of subsequences of this level, suppose it is Z, then the number of subsequences of this level, you can decide to append AI to it and it will jump to this level. So that's why you compute the number of subsequences of level L minus 1 and you promote it to level L. So in this manner, you can see that you solve the problem. Now, what is the time complexity for this dynamic programming? So you will realize that the the time consuming part is this: iteration over all the levels that are greater than it and then multiplying a range by 2. So if this is your DP array for the levels, so you are locating the first element that is bigger than x, and each element in this range you want to do, for each element you want to multiply by 2, and then you also want to find out the value located at level n minus 1, right? So you want to find out the value present at this location. So to optimize it, and that is why the time complexity is O of n into n, so O of n square. So if you want to optimize it, you just need a data structure that can do range multiplication and point queries, and that is nothing but a lazy segment tree that you can use from the AtCoder's segment tree library. So we'll just use that as a black box. So first we define a lazy segment tree that can do a range product and point query. So we don't need range updates, right? So that's why this is just a dummy implementation, and we just need range product, right? Multiplying things in a range by a given value. So that's why we define this mapping and composition. This is very standard. And then we do the same thing. We iterate over all the elements, and when it is time to append this element, and instead of manually iterating the entire range and multiplying by 2, we use the segment tree to multiply the entire range by 2, and we use the segment tree to query this point value. So now the time complexity is O of log n for each append that you do. So overall time complexity becomes O of n log n. So in this manner, you can solve the problem of finding all the subsequences that creates this same set of increasing order blocks, where the number of blocks should be equal and should appear in the same order. So this was the video, and there is also a part 2 of this video, and let me know if you want me to create that part 2. So in the part 2 of the video, we want an algorithm that can do something more complicated than this. So right now we have looked at this, and we have considered all the levels for the prefix maxima, right? Now if I ask you to solve this problem for a suffix maxima, you would also be able to do that, right? You can just reverse the array and then do the solve the problem. But what if the problem says that you have to find all the subsequences? Let me write that down. So the challenge question is find all subsequences where the prefix maxima and suffix maximas are equal. So this time you don't just have to satisfy the condition for the prefix maxima, and by that I mean the unique element. You also have to satisfy the condition for the suffix maxima, and you have to ensure that they are equal at the same time. So even if you look at the element from left to right, it should create this level, and this level, this set of elements in this level should match the original array. But even if you were to look at it from right to left, it will create some new set of levels, and this should also match the original array. So how do you solve this problem? So this is the harder version of the problem. Now let me know if you are able to solve this problem, and if you are interested in learning the solution to this problem. Maybe someday I will add the video for this problem as well.